Okay, today we're going to be talking about section 7.2 for the notes. Our first objective is we want to be able to calculate the mean and the standard deviation of a sampling distribution of a sample proportion. Okay, so today is all about proportions. And we remember that a proportion can be expressed as a percentage, a decimal, or as a fraction. Typically, we use decimals or fractions as we go through them. A couple things that we've talked about. All right, P we know is our population proportion. It's our parameter. P hat is our sample proportion. So your sample size is N and the number of successes is X. We're going to use Q hat as I go through things, which is really 1 minus P hat. Or you can also have P and Q. So a note you want to make that if you have P, the population proportion, that plus Q add up to 1. All right, so for population proportions, it's P plus Q is equal to 1. If it's sample proportions, then it's P hat plus Q hat equal 1. So the appropriate P adds with the appropriate Q to always equal 1. P is success, what you're looking for in the problem, and Q is failure, what isn't what you're looking for in the problem. All right. When we've got a sampling distribution, remember we had this example before. Now this was cousins, so this would be a type of an average problem. But let's say we had this scenario and it was percentages. All right. Let's say it's the percentage of I don't know, blue-eyed people. Right. I've got blue eyes. So if it's 10%, if we're looking for the true proportion of people with blue eyes to be 10% of the population, then this could be a sampling distribution. And I actually just crossed that off, but I wanted to keep that. This I had said was 16 samples of size 15, which means that there are 16 dots, and each dot represents the proportion of 15 people's responses. So you ask 15 people, what percent of them have blue eyes? Here's a dot. You ask 15 people, what proportion of them have blue eyes? Here's a dot. So this is our sampling distribution of the proportion of people who have blue eyes. Okay. If we want to find the sample distribution of a sample proportion, what we want to do is we want to choose a simple random sample of size N, okay, from a large population with a population proportion P having some characteristic of interest, like what I just said with the blue eyes. Then we can say that the mean of your sampling distribution of the proportions, you can have an average of a bunch of proportions. So the mean of P hat, your sampling distribution, is equal to P. This is important to remember. The other thing is that the standard deviation of your sampling distribution of P hat, we're going to write as sigma sub P hat. And that equals the square root of P, parentheses, 1 minus P, or Q, over N. Note, this is all inside the square root, okay? And it's P and Q. It's not P hat, Q hat inside here. It's P and Q. So whatever note you need to make. These are both on your formula card. If you take a look at your formula card, the Roman numeral 3 on the back, right here, for one population, the mean of P hat is equal to P. The standard deviation of P hat is equal to here. All right, we'll get to this later. So right now we're using these two formulas as we're working through this lesson. All right, so we'll talk about actually how to calculate those in a few minutes. All right, so the next guy is we want to talk about our conditions that we have to check. Just like in the last example, we had to check some conditions, or like back when we did binomial distribution. So we have some conditions we need to check here. You always need to check both of these, okay? The first is your 10% condition. We need to make sure that in order to use sigma sub P hat, in order to use this formula, you have to check the 10% condition. We need to check to make sure the population is at least 10 times your sample size. Remember, capital N represents population size. So in order to use sigma sub P hat, you have to check if your population is at least 10 times your sample size. For the large counts, right, this is the other condition we're going to use. we're allowed to use the normal curve if n times p is at least 10 and n times q is at least 10. So if n times p is at least 10 and n times q is at least 10, then you're allowed to use the normal curve. You have to check both of these each time. All right, so first thing I want to do is I just want to talk about like parameters and statistics and go through that like as a little recap from before. All right, so for this first example, voter registration shows 68% of all voters in Indianapolis are registered as Republicans. To test whether the numbers dialed by a random digit dialing service are really random, you use the device to call 150 randomly chosen residential telephones in Indianapolis. Of the registered voters contacted, 73% are registered Republicans. So question A, is the 68% a parameter or a statistic? So this one talks about the whole population, so it would be a parameter. Okay, and we would use P equals 0.68. The 73% are of the registered voters contacted, so that came from the sample. So that would be a statistic. Remember, parameters come from the population, statistics come from the sample. And we would have P hat equals 0.73. All right. It's important that you're able to identify this because as we cruise through the lessons, if you get these backwards, you're going to get all sorts of stuff wrong. Okay. If you had gotten these backwards when you do your standard deviation, you're going to plug the wrong one in here. Okay. So now what we want to do is we want to say what's the mean and the standard deviation of the sample proportion of registered Republicans in samples of size 150. If we do a sampling distribution and we repeat lots of samples, what would the average be and what would the standard deviation be? So the average of your sampling distribution is equal to P, which we just had as 0.68. Your standard deviation of P hat is equal to the square root of P times 1 minus P, or Q, over N. So we're going to get the square root of 0.68 times 0.32 over 150, and we get a standard deviation of 0.0381. All right, now, here's the key. In order to use the standard deviation formula, we have to check, is the population at least 10 times the sample size? Okay, so is the population of all registered voters in Indianapolis, I'm running out of room, is that at least 10 times 150 or at least 1,500, which is a reasonable assumption that that's true. Okay, so as long as that's a reasonable number, that it's at least 1,500, as long as it's reasonable to assume, then we're okay to use this approximation. All right. Part D now is saying, can we find the probability? What's the probability of getting a simple random sample of size 150 and getting that simple random sample to have a proportion of 73% or more as registered Republicans? Okay, so with that, what we need to think about is we're going to be using the normal curve. All right, in order to use the normal curve, we have to first say, can we use the normal approximation? Okay, in order to do that, we need to check n times p is at least 10 and n times q is at least 10. All right, so n times p, we're going to have 150 times 0.68 gives us 102 is at least 10. That works. I'm going to come over here. I'm going to say 150 times 0.32 gives me 48 is at least 10. And yes, that works. So since both of these work, then yes, we can use the normal approximation. So we just did that check. Now let's talk about what the normal curve will look like. All right? What goes in the middle of the normal curve each time? The mean. The mean is back up here. The mean is 0.68. All right? We want to know what's the probability of getting a simple random sample where there's 73% or more. So we want 0.73 or higher. We want up here. Okay. So when we look at this problem, we can use norm CDF to solve it, right? It goes lower bound, upper bound, mean, standard deviation. The lower bound is where the shading starts, 0.73. The upper bound is where the shading stops, infinity. The mean is 0.68, and the standard deviation is what we found here, 0.0381. And when you put that into your calculator, that should equal 0.0947, or a 9.47% chance. Okay, usually we leave our probability as a decimal, but that's really what it's representing. So now here's the question. How well is your random digit device working? We thought it would be 68%. We got 73%. There's a 9.5% chance that this happened by chance alone. Okay, which means the random digit service is working okay. It's not bad. We're not that far off of what we thought. There's an almost 10% chance that we'll be that far off, and that can happen, right? 9.47% is not terrible, but it's also not great. It could happen. Remember, just like we talked last chapter, 1% is very unlikely. 10% can happen. All right. So example 2. All right. The superintendent of a large school district wants to know what proportion of middle school students in her district are planning to attend a four-year college or university. Suppose that 80% of all students in her district are planning to attend a four-year university or college. What's the probability that a simple random sample of size 125 will give a result within 7 percentage points of the true value? So if the truth is P equals 0.80, we want to go up or down 0.07 from that, 7 percentage points. So what we want is we want to find the probability that 0.73 to 0.87 is where our P hat is going to lie. 7 points higher and lower than 80%. Okay, we know that our mean of our sampling distribution is equal to P, so that should be 0.80. Okay, we need to check, is our population at least 10 times our sample size in order to use our standard deviation. So is our population at least 1250 is the number of students. Now, since this problem said a large school district, then I would say that's reasonable to use. Okay, so our first check, that's reasonable, which means that we can now figure out that the standard deviation of the sampling distribution is equal to P times Q over N. So we get 0.036. All right, we also need to check for the normal curve. So we also need to check for the normal curve. We need to check, is N times P at least 10, and is N times Q at least 10. All right, so we are going to have 125 times 0.8 is 100. And then we're going to have 125 times 0.2, which gives us 25. Both of these pass, which means it's okay to use the normal approximation or the normal curve. So now that we know that, we can jump into the normal curve. What is our normal curve going to look like? In the middle goes the mean, which is 0.80. We want 7 points higher and 7 points lower. So that's where our 0.73 and 0.87 are going to lie. All right, we're going to use norm CDF, lower bound, upper bound, mean, standard deviation, right? Make sure you label them underneath, and that will give us an answer of 0.9482. That's our probability. Now let's talk about how to summarize this, okay? And I've got this right here. To summarize this, it's going to say about 95%, right? 0.9482 is 95%. About 95% of all simple random samples of sample size 125 will give a sample proportion within 7 percentage points of the true proportion of middle school students who are planning on attending college. Okay, this is going to represent the probability of meeting what we thought it was. We're looking for what's the probability that a simple random sample of size 125 will give a result within 7 percentage points of the true value. So what I had just shown you here, if you need to pause, pause. This is a way to interpret our answer, because remember, it's half calculate, half can you interpret what you calculated. So on the next page, you guys are going to have that example up top. What I want you to do is I want you to pause the video, try this on your own. Oops, over here. Here we go, Ms. Michael. Try example 3 on your own. Okay, pause it, see if you can get all the pieces, and then take a look at here. Here's my work. Okay, here's my checks. Okay, these 3 dots mean therefore or conclude. Right? And then here's my calculation and my answer. Alrighty. So then the last thing we're going to do is we want to talk about why we can't use these methods. Let's break some stuff down. If we've got a factory employs 3,000 unionized workers, of whom 30% are Hispanic, the 15-member union executive committee contains 3 Hispanics. What would be the probability of 3 or fewer Hispanics if the executive committee were chosen at random from all of the workers? So what we need to do is we need to check, is our population at least 10 times our sample size? And we need to check N times P and N times Q. So go ahead, pause that, and see if all of our checks work. And when you unpause, hopefully you found that N times P at least 10 doesn't work. 15 times 0.3 is 4.5, and 4.5 is less than 10. So we can't use the normal approximation because we failed that check. All right, it didn't work out. So again, this time, read this problem and check population at least 10 times your sample size, N times P at least 10, N times Q at least 10, and then unpause, come back to me, and you would have found that your population is not at least 10 times your sample size, right? If you have 10 times 50, we don't have 500, okay? So if we said that it's not reasonable, okay, for our population to be at least 10 times our sample size. Okay, we only have 316 athletes. We needed it to be at least 500. Now, here's the trick. How would we do this? And this would be example 4. Okay, using the methods from chapter 6, what we just tested on recently, we want to find the probability for this here. Okay, this problem back here was actually what kind of problem? We couldn't use the normal approximation to do the probability, but we have a fixed number of trials, and we have success and we have failure, which means it's a binomial problem. We could have had N being 15, P is 0.3, and X we want to be 0 to 3. So this guy actually would have been a binomial problem. So we would have had binom CDF of N, P, lower bound, upper bound, and 0.297 should be our answer. Okay, good job today taking great notes. Here are the practice problems. I'll let you know in Google Classroom if you're supposed to do these right after watching the lesson or if we're going to work on them during some class time. I'll specify, but there's never a harm if you want to get started ahead of time. There's actually not a whole lot of them. Good job today. See you soon.